For today's seminar, I will explain about a journal from International Journal of Production Research titled Dynamic Scheduling of Wafer Batch Processing Machines via Reinforcement Learning, enhanced by Expert-Guided Lightweight LMM. First, I will explain why wafer fab scheduling is a difficult problem. First, wafer fabrication environment is highly dynamic. Jobs arrive randomly, the process flow is reentering, and machine's conditions can change anytime. Because of this, the schedule must be updated online in real time, and decision made earlier can quickly become outdated. Second, many machines are batch processing machines. That means we cannot simply process one lot anytime. We must consider batch capacity limits, product compatibility, and the precedence between layers. So, decision only is not only about choosing the next job, but also checking whether the batch is feasible or not. Third, scheduling creates a very large coupled decision space. At each decision point, we must decide how to form batches and assign them to the machines at the same time. This combination causes a high dimensional action space, making global optimization extremely hard. The paper this paper proposes a multi-agent collaborative reinforcement learning framework to schedule wafer batch processing machines under highly dynamic conditions, where jobs arrive continuously, constraints are complex, and wafer flows are routine. Because traditional rules struggle to make globally good real-time decisions, the author designed an RL-based scheduler that can adapt online. To simplify the decision making, they split the problem into two cooperative agents: a batch formation agent that groups lots into batches, and a batch assignment agent that dispatches batches to idle machines. This reduces constant coupling between batching and assignment, making learning more stable. They further integrate a light LLM as semantic guidance to recommend balancing actions. The LLM is trained using two-stage fine-tuning. First, with expert knowledge, so it learns feasible and reasonable scheduling patterns instead of random exploration, and then with RL experience, so it improves based on actual performance under dynamic arrivals. Finally, a transformer-based Fusion module helps the agent share information and coordinate decision. The goal is to minimize average task flow time while improving equipment utilization. On this slide, I summarize traditional scheduling approaches for wafer batch processing. First, many fabs use rule batch dispatching, such as FIFO and EDD, because it is simple and fast. However, these rules rely on fixed logic, so they often lack adaptability in complex settings with reentrant flows and strong batch interactions. Second, researchers apply heuristics and method, such as uncloney optimization or proximity search methods to explore better solutions beyond fixed rules. These methods can work well in static environment, but they often generalize poorly when job arrivals are random and the system changes dynamically. Overall, rule-based and heuristic methods are insufficient for real-time dynamic over batch scheduling, which motivates learning-based approaches such as reinforcement learning. On this slide, I summarize research that motivates this paper. Reinforcement learning has been widely used in dynamic scheduling because it can adapt to uncertainty like random arrivals and time varying conditions, and it has shown potential even in reentrant wafer processes with complex setups. However, multi-agent RL becomes much harder in wafer batch tools due to high dimensional state and action space, which can lead to local optima. Weak understanding of long-term dependencies and poor inter-agent coordination under dynamic and reentrant flows. To improve coordination, recent studies adopt transformer-based attention, which help agents share information and capture long-range dependencies more effectively. Another direction is using LLMs as guidance modules, since they can recommend more reasonable actions through contextual reasoning. But large LLMs are often too costly for real-time industrial use. Therefore, this paper bridges the gap by combining collaborative model, transform-based coordination, and a light rail LLM for semantic action guidance, aiming for practical real-time wafer batch scheduling. Here is the system overview of the wafer batch scheduling. First, lots arrive dynamically, including both new release lots and re-entrant lots that return after completing a layer. The scheduling process involves two key decisions. Decision 1 is assigning incoming lots into two buffer slots to form feasible batches. Decision 2 is assigning the form batches to available batch tools, which are modeled as three parallel machines. After processing, lots move to the next layer and may re-enter the system again, so the environment is continuously changing. On this slide, I explain the decision variables used in the mathematical models. These variables represent the two main choices the scheduler must make. First, why IWM is a binary assigned variable. This tells us which machine processes a specific job at a specific layer. For example, if YIWM equal to 1 means job I at layer W is assigned to machine M. If YIWM equal to 0, it means it is not assigned to that machine. And next, XRR prime represents whether a setup is required due to a recipe change. Here, R is the previous recipe type the machine was running, and R prime is the new recipe type needed for the incoming batch. And for example, if the recipe is different, R is not equal to R prime, it means the machine needs a setup, so setup time penalty is added, resulting XR and R prime value equal to 1. If the recipe is the same, R equal to R prime, then X value will equal to 0 because no setup penalty or no penalty, no setup is required. So the role of this variable is to detect recipe switching, which is important because in wafer fabs, changing recipes creates additional setup time and reduce efficiency. On this slide, I summarize the mathematical model used to describe the wafer batch scheduling problem. First, the objective is to minimize the average flow time. Flow time means the total time a task spent in the system, including waiting and processing. So minimizing means we want jobs to finish faster on average, which improve efficiency and reduce congestion. Next, the model includes several key constraints. The first constraint ensures assignment feasibility. Each job layer must be assigned to exactly one machine, so every task is processed somewhere. The second constraint is the batch capacity constraint. For each machine, the total number of tasks assigned cannot exceed the machine's maximum batch size. After that, the model defines how processing and completion time are calculated. The processing time of a batch is assumed to be equal to the processing time of task at that layer. The completion time is composed of multiple parts. The task ready time, waiting time, actual processing time, and additional overhead such as transfer time and handling time. This equation basically captures that a job may not immediately start processing. It may need to wait, or it may also require extra time if there is movement or setup overhead. Then, The constraint enforces the process order. A job can only arrive at the next layer after it completes the current layer. This is important because for reentrant flow, the wafers move step by step through layers. Next is the expected completion time of batches on a machine is defined sequentially. The first batch of completion time includes its processing time plus a basic overhead. For later batches, the completion time depends on the previous batch completion time, meaning the machine processes batches one after another. So these formulas describe the machine as a timeline. Batch 1 finished first, then batch 2, and so on. Finally, the predicted flow time estimates how much time a lot still needs to finish the remaining layers. It includes the time already spent since release plus the remaining processing and handling time. So overall, this mathematical model describes the objective, feasibility constraints, batch capacity, and how much time involves across machine and layers in a reentrant buffer environment. This framework solves buffer batch scheduling using collaborative multi-agent RL. The environment is dynamic and reentrant, so the decision must be made continuously. The method is two agent, one agent form batches, form batches when lots arrive, and the second assign batches when machines become available. To avoid learning independently, a transformer module shares information between agents to capture long-term effects. In addition, a lightweight LMM provides thematic guidance by recommending reasonable action candidates, which improves convergence and stability. On this slide, I explain the state space, meaning what information each agent observes before making a decision. Since the framework has two agents, each agent receives a different observation depending on its role. First, the batch formation agent makes decision when a new task arrives. So it observes information about the incoming task and the current batches, the current batch buffer slots. That is why its state is represent as F1, F2, which means task related features plus batch related features. Second, the batch assignment agent makes decision when a machine becomes idle. So it observes information about the candidate batch and the machine status. That is why its state is represented as F1, F3, which means batch related features plus machine related features. This is the action space for both actor RL that can choose any valid action and action space for LMM, which gives recommended candidate actions as a guidance or as semantic guidance. For example, batch formation agent actions will choose which batch buffer slot K to put the arriving lot into. Or if there is no feasible slot or the buffer is full, the agent will choose to wait. And second, batch assignment agent actions, it will choose which batch goes to which idle machine that symbolized as M. And if there is no machine available, the batch assignment action will choose wait. Next is the reward function. Because we have two agents, the reward is also split into two parts. First, reward for batch assignment. This reward encourages the assignment agent to choose a batch machine decision that improves system efficiency. In simple terms, it gives higher reward when decision reduce waiting time, increase batch fill ratio, and keeps machine utilized. And it gives penalty for bad decisions like excessive waiting, low utilization, or unsuccessful grouping. Second is reward for batch formation. This reward focuses focuses on forming batches that can start processing earlier. So it encourages the formation agent to reduce machine idle time and build batches that allow an earlier start time. Global penalty for constraint violations. Finally, the total reward combines both parts. The last term is a global penalty that strongly punishes constraint violation, such as batch exceeding capacity, incompatible lots in the same batch, or precedence violation. So, the rewards design balance efficiency and feasibility. This slide explains how the authors construct data to fine-tune the Lightwell LMM. The main idea is they want the LMM to behave like an expert scheduler, so they create an expert style dataset in a structured format. First, they define the scheduling task, such as batch assignment, and describe what information should be considered, like equipment status, compatibility, urgency, and reentry. Second, they use a prompt template to provide the LMM with the current system situation as input. This input includes machine information and wafer task information, such as queue, status, recipe types, capacity, waiting time, and priority. Third, they add decision constraints like equipment must be idle, recipe compatibility must be satisfied, urgent tasks should be prioritized, and batch capacity limits cannot be violated. Finally, the expected output is an expert decision in a clear format. For example, which batch should go to which machine and which tasks remain unassigned. So overall, this process generates expert decision examples, are used to fine-tune the LMM, so it can later provide reasonable candidate actions as guidance for reinforcement learning. This figure explains how the two agents interact and coordinate using a transformer. At each step, the batch actor and the assignment actor each observe the current environment state and make their own decisions, one for batching and one for machine assignment. Both decisions are then evaluated by a global critic in the middle. This global critic provides a shared learning signal, so the agents are trained to optimize the overall system performance, not only their local objectives. The transformer module on the top works across time steps. It aggregates and selects important information from historical states, producing a shared container representation, or symbolized as empty. This helps the critic and agents capture long-term dependencies such as waiting history, setup changes, and reentrant effects. So, overall, the transformer improves coordination by providing shared global context, while the global critic ensures both agents learn toward the same level objective. This slide shows how the authors tune the hyperparameters of their framework. Instead of trying every single possible combination, they use 7-factor, 3-level orthogonal design, which is an efficient experimental method to find good parameter setting with fewer trials. The goal is to minimize total flow time, since lower flow time means better scheduling performance. They tune parameters from both parts of the system, RL tuning parameters such as actor learning rate and the global critic learning rate, and LMM, LLM related parameters such as LMM learning rate and weight decay. They also tune structural parameters like number of batch buffers and the interaction factor length. Each plot shows how changing one factor affects total flow time, and the red boxes highlight the best performing values. This table explains how the author generate benchmark test cases for their experiments. Instead of using only one fixed scenario, they create multiple cases by changing key factors that control the difficulty of the scheduling problem. They vary the number of machines, the number of tasks, and the job arrival patterns where arrival follow a normal distributions. Hence, controls the average arrival rate and control how random or busy the arrivals are. They also randomize the processing time using a uniform distribution. So overall, combining these settings, they can create different complexity level from simpler cases to more challenging dynamic cases and evaluate how robust the proposed method is under different conditions. This table shows the main benchmark results. Each row represents a different benchmark cases created by different parameter combinations such as number of machines, number of tasks, and arrival randomness. The main performance metric is the mean flow time in minutes. Lower mean flow time means the scheduler finish jobs faster on average, so it is better. In the table, the hours column is the purpose method and it compares against two baselines, MAC, which multi-agent collaborative RL without LMM, and GSACO, which a heuristics optimization approach based on end colony search. The both values indicate the best result in each row. Overall, the proposed method achieves lowest mean flow time across most benchmark cases, meaning it gives the best scheduling performance. In addition, the variance and 95% confidence intervals are generally smaller, which indicates the results are also more stable and consistent, not only good on average. These figures visualize the benchmark result. On the x-axis, each group represents a different parameter combination. On the y-axis, we compare the average flow time and lower is better. The green bars are the proposed method, while the blue and the seen bars are the baseline, MAC and GSACF. Across almost all cases, the purpose method consistently achieves the lowest flow time, which means it schedules slots more efficiently and reduces waiting. Another important point is that the improvement becomes more noticeable in the more difficult or larger scenarios, which suggests the method has better scalability and robustness under complex decisions. This slide is an ablation study to check the impact of the LMM guidance. They compare two sightings with LMM guidance versus without LMM guidance. On the left, the flow time curves show that with LMM guidance, flow time drops faster and richer to lower level. This means jobs finish faster and the system has less waiting. In the middle, total reward is higher when using LMM guidance, which indicates the agent learns a better scheduling policy and converges faster. At the bottom, GPU usage is slightly higher than the LMM, slightly higher with LMM, because generating candidate actions adds extra computation. However, the increase is not extreme, so it remains practical for training and still stable. The next ablation study explains why LMM guidance improve scheduling using a Gantt chart example. Each row is one machine, and each block represents a batch being processed over time. The first observation is less machine idle time with LMM guidance. In the RL only schedule, there are more gaps between batches, meaning machines wait longer. With LMM guidance, the batches are packed more continuously, so utilization improves. Second, the LMM guide schedule shows more consistent batching. The batch size looks less fragmented, meaning fewer half-filled batches and more efficient batch formation. Third, the schedule across machines looks more balanced and coordinated. Instead of one machine becoming overloaded while another is idle, the LMM guided strategy produces a smoother overall structure. So overall, this figure shows the LMM helps by generating better candidate actions, which reduce idle time, improves batch quality, and coordinates the system more efficiently. This slide compares three lightweight LMMs used as the guidance module. First, LLAMA 38B, Kemma 2B, and Pi 3 Mini. On the left, we look at the flow time, where lower is better. Pi Mini drops faster and reaches a lower flow time earlier, meaning it helps the agent learn good scheduling decisions more quickly. On the top right, we compare total reward, which reflects overall policy quality. Pi 3 Mini shows a smoother increase and stabilize earlier, suggesting more stable learning compared to the other models. On the bottom, after loss curve also indicates training stability. Pi 3 Mini shows more stable convergence, while Llama 3 8B has larger fluctuation and slower stabilization. So overall, Pi 3 Mini performs best as the lightweight guidance model and improves learning speed, yields lower flow time, and provides more stable training compared to Gamma 2B and Llama 3 8B. The next ablation study is about how different information sharing mechanisms affect collaboration between the two agents. They compare three settings. First, without interaction, the pink one, the agent acts almost independently, meaning there is no coordination. LSTM fusion, the orange, agent shares information through sequential memory, but it has limited ability to capture long-term dependencies. Third, transform fusion, the blue or green. Agents share information using attention. So the model can focus on the most relevant parts of the history. Now, looking at the result, in the flow time plot, transform fusion reduces flow time faster, meaning better scheduling efficiency. In the total reward plot, transformer achieves higher and more stable rewards, showing stronger coordination and more stable convergence. In after loss plot, transformer produce lower loss, indicating smoother and more stable training. So overall, this confirms that transformer-based fusion improves agent collaboration by capturing long-range dependency and preventing unstable behavior seen when agents do not interact. This slide describes the simulative wafer fab route used in the case study. The table shows the main process steps within one layer, such as wet process, diffusion, photolithography, etching, wet process, ion implementation, wet process, thin film process, and metallization process, along with their processing time ranges. A key point is that this fab is reentrant. After completing one layer, wafers repeat the same route again for the next layer, so jobs return multiple times, and the system becomes highly dynamic. In this route, the diffusion furnace is the main batch processing step, and it becomes the bottleneck. Because diffusion is slow and processes lots in batches, decisions About batch formation and batch to machine assignments strongly affect waiting time and flow time. So this case study represents a realistic and challenging scheduling environment with repeated arrival and batch processing constraints. This table explains about the sequence-dependent setup times. This table, in detail, explains about a setup time matrix between wafer types. Each value means extra setup time required when a machine switches from processing type I to type J, for example. The diagram. This matter for scheduling because frequent switching between different machines types increase setup time, which creates machine downtime and reduce throughput. So the goal is not only to minimize waiting, but also to reduce unnecessary recipe switches by forming more compatible batches and choosing assignments that keeps the machine stable. This is also where the LMM guidance helped, because it can recommend more expert-like batching decisions that avoid inefficient switching. The figure 10 shows the case study's results by comparing average flow time and computational runtime across 10 simulation scenarios. The bar represents the average flow time. Lower is better because it means lots finish faster. The lines represent runtime. Lower is better because it means the method is more practical for real-time scheduling. Across most scenarios, the proposed method achieves the lowest or nearest lowest flow time, meaning it provides the best scheduling quality. At the same time, the runtime stays relatively stable and reasonable even when the scenarios become larger and harder. So it shows good scalability. Compared to the baselines, some methods either have higher flow time or their runtime increases sharply as complexity grows. So overall, the proposed method provides the best trade-off between scheduling, performance, and decision efficiency, which is important for online fab control. This table, this two table, checks whether the scheduling decisions are fast enough for real-time operation. They compare the decision against attack time 0.33 hours or equal to 20 minutes per scheduling cycle. The proposed method has median latency around 11 seconds and 95th percentile, 95th percentile, about 24 seconds. So it is very small compared to the 20-minute cycle. The violation rate is only 2%, meaning in most cases, the method makes decision fast enough for online scheduling. So overall, this slide confirms the method is not only accurate, but also robust and practical for real-time fab control. To conclude, this paper proposed a lightweight LMM-guided multi-agent RL framework for wafer batch scheduling. The scheduling is decomposed into two cooperative agents, one for batch formation and one for batch assignment, and they coordinate using a transformer page fusion module. By using the LMM as an expert-like guidance module, the method learns faster and makes better scheduling decisions. As a result, it achieves more than 20% flow time reduction in benchmarks and around 25% improvement in practical scenarios, while also improving utilization and robustness. Finally, here are the limitations. First, the method is validated in simulations, so it still needs real factory deployment to fully prove practicality. Second, scalability can be challenging when the state and action space becomes very large, especially with more complex constraints. Third, the current work mainly focuses on flow time, so the scope can be expanded. And this is my opinion about this paper in terms of strength and weaknesses. First, the main strength is that the paper targets dynamic wafer batch scheduling, which is a really an important problems in semiconductor labs. Second, the author validates the framework through many experiments, including benchmark results, ablation studies, and case studies, which makes the result more convincing. And third, I also think the paper explains each component in very detailed steps, so it's easier for readers to follow the whole method. However, there are also some weaknesses. Even though each section is detailed, sometimes the flow between sections feels not well connected, and it it feels like they repeat the previous section. Also, since they use an LMM as guidance, the paper does not clearly explain how they control hallucination or unsafe suggestions from LMM, which is it can lead to some dangerous actions. And if in the paper stated like how they prevent hallucinations from the LM, I think it would be better. Finally, the framework combines many components, multi-agent like RL, transformer fusion, and LMM guidance. So in real factory deployment, it may be harder to maintain, tune, and implement compared to simpler methods. That is all from me. Thank you very much for listening. See you in another seminar.